Okay, good morning, everybody. First of all, a thank for the organizers of inviting me here today again. I was here two years ago, and I enjoyed this conference a lot. It's always nice to be here. It's living nearby the border in the past when I was young. Nearby Roosendaal, somewhere it's coming back home. But of course, when we play football and do cycling, then there's a difference between the Netherlands and Belgium, of course. As long as you know who's number one on the ranking of the best football team in the world, that is okay. Then we are friends. Okay, also nice to see alumni from everywhere, and the programs we have, either from Lund or from Ghent or from our international master, so it's always nice to be. And as I said, it's coming back a little bit home, and then on the other hand, you've been nice to do the climate in this room a little bit to Scandinavian properties, to a little bit colder, so maybe that was also the reason why it was done. I will talk a little bit about ventilation systems, and it's connected a bit. Unfortunately, I couldn't be here yesterday, but I would have loved to see the presentation given yesterday on experimental tests on ventilation in buildings, smoke ventilation then. My talk will be a bit similar, but a little bit more maybe focused to the modeling. So I'll talk a lot about introduction and background, mainly that I see that everybody of you know roughly what the problem is and what the possibilities are to using, for instance, models in this field. And then I'll talk a bit about the modeling validations and so on, and also on a practical example or application on how we have done this, and then I finish off with conclusions. I think it's important that to know that the use of computational fluid dynamics in performance-based design is sometimes increasing in the area. And you've all been probably confronted with pictures which are similar, like here. This is just a flame spread or fire spread of a set of cable trays. That also means that if we use these models, then two things are very important. One, of course, is the let's say the verification, and that means simple terms, and that you have to ensure that the model has been correctly implemented, so that you have used it. So if I give a very simple example, if you would say 3 + 2 is 5, your model or your calculator, if we go back very much in the old days, then is really giving you 5 as a result, and that's the verification. And that's quite often something which, as a user, you don't worry about that so much, because that's up to the ones who developing the code itself. So I will not talk too much about that, but it's an important thing, because if something is wrong there and it has not been checked, you're not getting that value of 5. Simply, you can get maybe 4, and you don't want that in this simple example. The other thing is the validation, is that let's say your model is really appropriate for your physical problem. And here it's the same. I gave it very simple. I use this 3 + 2 is equal to 5. But if you want to know what 3 times 2 is equal to 6, and you use this calculator only doing the addition, that will not work either. So you use the wrong type of model, because your model can only do addition and not multiplication. So this is in a very simple way the difference between verification and validation. And in fire terms, in the fire model, that means that we have to somehow do this by experimental designs and seeing if you cover that. And that's an important thing. And I will talk a little bit more about how we did it with the ventilation models available for the moment. So that's an important part, and it's sometimes just jumped over. So we see a lot of examples where models are used where maybe this, especially this validation, is not being done in detail enough. So On the other hand, we also see somehow reluctance. It depends a little bit where you, in what field you are and what country you are, so maybe, but that these models maybe are considered, well, are they really robust? And especially after my talk, you're maybe going to say, well, I didn't feel them so robust, so should we really use them? But the most important thing is that we go forward, because in some way or another we should not stand still and wait what will happen, but we should be proactive. So we have to do this kind of research on modeling. And in the work we have done, and this is not a complete list, so you can surely when we are at the question session say, okay, should we not look to this? Then I will say certainly, of course we can do that. But these are areas where we have looked into 3 areas which are of interest if we look to a room or a multi-room scenario, which is here on the right. This is trying to predict the mass loss inside an enclosure instead of using tabulated values. That's one. And then, since we're using, and I go a little bit more into detail on why, you have mechanical ventilation trying to predict the fires inside an enclosure where you have mechanical ventilation as we would have here. At least you could feel that when we came in, that there's some ventilation cooling down this room. And then, of course, the building characteristics. That can be the insulation, but it can be the geometry on the fire growth or the fire behavior. I'll focus on this mainly on the mechanical ventilation, because well, that was the area where I was asked to talk about also. The 2 other areas, one of my students graduated last year, Jonathan Walquist, and he has written a whole PhD. So if you have problems sleeping from time to time, take that one and you can read to it, and then you have certainly literature for another 2 or 3 weeks in the evenings, all depending on how much interest you're in, because you maybe don't go to sleep, in fact. The problem is a little bit, as I said here, and this is a little bit of setup which in fact has been done tests on, where we would simplify it in the picture that you have a fire in the lower floor here. It will start producing, of course, smoke, and there is openings between that room and the room upwards. It's more an industrial application, I agree. And what happens is that you get, of course, buoyancy of this smoke in this room. But then, of course, somewhere there needs to be extractions and incoming ventilation in it. And what will happen, of course, that this fire will be depending on size on how much ventilation you have. And also, of course, the conditions in that room will depend a lot on the interaction of fire and ventilation. I'll come back to a bit more detailed explanation in a few minutes. The prediction of mechanical ventilation, why should you do it? And maybe you're going to say, okay, this is a full keynote lecture on mechanical ventilation. Is that important? The first, of course, is we get into, I've not gone into details exactly on examples. We go more to energy-saving buildings. And we go from a lot of natural ventilation towards mechanical ventilation. Why? We want to have our buildings tight, because we don't want to get heat escaping out of the rooms through leakages. So we want to keep it as much as tight, and that means if you want to survive there and get oxygen, of course, you need some ventilation coming in, and you have to define standards how much this ventilation would turn around. And you feel that sometimes these days in certain office rooms or public rooms that this ventilation is important, because if we don't have enough, let's say, oxygen, we will get not working as good as we get a bit tired, you get a bit sleepy, and so on. So this mechanical ventilation should be enough. So if we talk about residential housing and so on, these systems, they are quite complex. They are sometimes shared over different compartments, and all depending on the regulation. Maybe one apartment is a single fire compartment, and then you don't want to have spread only to the ventilation system. And you have a whole bench of testing to be done, but you also have to check if that works. And there's a lot of technology on how to solve that. That's the residential area. The area where we worked mostly in, and I'm going to give most of the examples, is of course the power, nuclear power industry and process industry, where you have mechanical ventilation. There you don't want to have, in case of an accident, a lot of, let us say, leakage to the outside world, because it could be radioactive. So they had a long tradition of using mechanical ventilation. And the first power plants, nuclear power plants, were not as tight as the new ones which are built. The new ones are almost like tight concrete rooms where we don't have a lot of leakage. So what can happen, of course, is that, and this is just a simple simulation of a fire where you get an inlet and you have an outlet. And what's happening if there's a fire, of course, the fire will start, and let us say simply it's a pool fire to make it easy for us. Smoke will start generating. It will go out of the exhaust system because it will be extracted, and you will get air coming in. And then, of course, what's happening is that you all know that the fire gases will expand and they will create pressure. And that pressure, of course, will be in that room. And what can happen now, of course, is that the first thing is that this pressure becomes too big that the air which comes into your room will be worked against that kind of pressure, so that you will push even smoke through the inlet because the pressures get too high. And why do the pressures get high? It's because you have a tight room. There's no escape for the smoke apart from the exhaust, and the exhaust is mechanically steered. You cannot control it because it's the fans. And quite often the fans, as you don't want to go too much in the technical details, they are somehow also depending on capacity and the temperature of the smoke and so on. So that happens. So the inlet somehow disappears. Can go down. It can even be smoke leakage. And what does that mean for the fire, of course, you will say? Yeah, well, you don't have enough oxygen anymore. So the fire somehow will start to starve and to reduce. You will get an underventilated fires, and then depending all on the type of extraction and inlet and outlet ventilation, you can get a situation where this is going back and forward. It's like a breeding fire. In one case, it can be also that it just starves because the oxygen is gone. And that's something where there have been a lot of experiments done in this project, which I will explain about. So the problem is connected to the nuclear power plants, and it would be not fair to quickly say it, because there are happening fires in nuclear power plants, as you all might have noticed. It's about the frequency 10⁻² per reactor year if you see it over the whole world. And they use quite a lot of probabilistic risk analysis and CFD modeling. And of course, then they want to be sure that if they use these tools, that they are working also. Well, because the consequence can be disastrous if it's not correct, partially on leaking out maybe radioactive smoke, or even spreading the fire inside the facility, and avoiding, which is the major problem in case of a fire for a nuclear power plant, is not being able to shut it down because there's no redundancy anymore. So there's a lot of need for data, and a lot of this work has been done, and so I don't want to take credit for what we have done only, is the so-called Prisma project. I will give you later the link to this project and to the outcome of this project, which is, I'm not going to use the French, but it's fire propagation in elementary multi-room scenarios, and it's mainly focused on mechanical ventilation. And in this area, I focused a little bit on this was a quite big project. It's almost had, I think, a budget of 15 to 20 million euros. So it's an OECD project. They sponsor a lot of research in the nuclear power sector. So one of the things they studied was the propagation of heat and smoke from fire from one room to adjacent rooms. Looked also to impact of that related to critical system, and now we talk about cables. Cables can be, on one hand, their, let's say, fire source, but on the other hand, they can be the target in case of a fire. I explain that simply. One cable maybe steers a pump for, let's say, safety actions in the reactor area, and that cable has to function when there's a fire. And that's a big problem for the nuclear power plants to know that. So that was part of the project also. And then, of course, the impact of the ventilation in limiting heat and smoke propagation. They did in totally, I think, 35 large-scale tests. You will see later the setup. These were not also small-scale tests. And on top of that, there was modeling of these tests by different groups. And I'm sorry that Simo Ostika left, but he was involved in that project also, so and in the modeling. So on the other hand, it's an advantage for me, so I cannot get at least one tricky question from him. An example here to explain you how this mechanical ventilation can affect the fire. This is just let's say a mass loss rate, or you can call it also, if you combine it to the heat of combustion to heat release. The red line is in an open configuration of cable trays. Let us say 3 cable trays starting to burn and going to a mass loss rate of about 17 grams per second. So I think, if I remember well, it's then in the order of maybe 300 or 400 kilowatts. The blue line is when you have 15 times the renewal of the air in that room. The green line is when you have only 4 renewals. So you see what's happening going from this to the blue line to the green line. You reduce the mass loss rate because you almost, for the ones who like to calculate, you can almost calculate how much oxygen is coming in and how much that will give as a heat release. And that will be the limiting factor if everything goes perfect. But everything, unfortunately, is not going perfect, like is always with fires. What's happening if we go down, you see this peaks up and down. And that doesn't mean here that the computer didn't like the measurements anymore and started to measure up and down mass loss rates. No, it's really that the mass loss rate is going up and down because you get a kind of a breathing or a back and forward of the mass loss rate. And that is, and if I try to push it towards, let's say, I've seen now on the mentometers that it's about 40–50% fire brigade here, because I could see that on some of the results. What does that mean? These fires you don't like because you don't know what's happening. They are under-ventilated. And if you open, you all probably know much better than me what can happen. So this mechanical ventilation, if we have this very tight rooms, either it's a nuclear power plant or it's in residential areas, can lead to very risky situations for the fire brigadier. So we need to know the knowledge what would happen in case of a fire. This is just an example where we started the project on modeling, and it's just to give you an idea. It's not meaning that you have to understand everything in this slide, but this is a single room with mechanical ventilation and the prediction of mean temperature locally and global during a steady state of these type of tests. These are the depths which are considered that this is the error in the measurements, and the bars are different models, different groups of doing modeling. So in certain cases, 0.4 means about 40% of an error of a simulation where the people knew the data in advance, so they couldn't get closer than that. It's not that they didn't know the results beforehand, because that's to me, it's really that they knew the data. You see that the errors are similar, and all the colors are different models and different groups. So we felt that we should try to do it better at the end, and so that's why we worked on this ventilation model. quickly saying is that cables are important, but are complex. You have different materials in that. I like a lot of cables because I've done a lot of research on that. I'm in the background electrical engineer, so but they are not easy to predict. So you go to a step where you use pool fires instead, which are maybe not as easy as you would guess, but especially also in the nuclear area, this is one of the sources. But it's possible to use it. And what you see in the picture here is typically a one room ventilated, mechanical ventilation with a pool fire, and that's what's happening if you have this, for instance, 15 times renewal of, you get a quite underventilated fire. In certain cases we had also even, which we could model but could not see because the video was just one black thing, but you had this kind of so-called ghost flames, that you had a flame here, you had a flame here and there. So not so funny and interesting but not funny fires. And this is what's happening here. You have mass loss rate, you have thermal expansion, there's an amount of momentum transfer, and I don't give any equations, I try to avoid that. There's convection and mixing, and then you also have phase change. So it's a complex physical problem where you can see that the pressure goes up, the mass loss goes up, then it goes down, as I explained. What happens with the pressure, that goes up and it goes down and gets unstable. And also with the Q atmospheric, which is the air into the room, it changes depending on the conditions. So it's a kind of an interaction. It's a kind of a war between the fire and then the ventilation, and back and forwards, and who's maybe win and loses. And this is of course challenging for everything. It's challenging for the building, but it's challenging for the ventilation system because it has to cope with that, unless you have actions, of course. So in the Prisma, and this was a problem in Sweden for us a bit to sell this project. We have a big nuclear power industry, at least still now. It will reduce, of course, also in Sweden. But we wanted to show that we could use this also in residential buildings. And of course, I agree fully, we don't have pool fires, at least not most of you are going to have a pool fire in your house if you have a fire. But it's a way to start working with it. But the problem of mechanical ventilation, and I repeat myself now a little bit just to see that you catch this important problem, is that you get this residential with mechanical ventilation more and more. And we're going to go to that in the future. And we need to control, let's say, the hazards for that. So the tests in the Prisma project or in the nuclear power plant, this is the setup. So we have in this project, it's the facilities of IRSN, which is the French Research Institute for Nuclear Power, and they have also a fire lab. It's near Cadarache in the Provence in the south. So it was not only an interesting area to meet, but also to see this laboratory, because they used, these are fully concrete rooms with a ventilation system which is a schematic here, but it's much more complex with shutters, valves, and so on. And in these rooms they could shut on and shut off ventilation a little bit how they wanted. So that was part of these tests. The test series were one room setups, multiple rooms. I only show the one room with intake and exhaust. It's a very, again, simple sketch of the problem. And the other thing where we had multi-rooms, there was leakage. The project is, as I said, an OECD project, so most, not all countries having nuclear power plants, and were both financing and supporting the project to research worldwide, so not only Europe. As I said, cables and pool fires were used, and we focus a bit on the pool fires here. I don't expect you to understand it, but this is a bit the so-called mechanical. And there's maybe a few ventilation engineers here, but it has, as I said, a complex system. And for the modeling, and I'm afraid to say that, you have to get that into your model. And that's not maybe the easiest and user-friendly part which FDS has now, because the FDS has a so-called HVAC module, which is a ventilation model, but it is not as user-friendly as the rest of FDS. So it's hands-on. It's typing in the notes. I can say that my PhD student suffered a lot to get that into the system, but it was the only way, to be honest, to get the prediction which was acceptable. Otherwise, it was a bit like we started in the beginning. You get this spread of results depending on how you had solved the problem. Results. This is an example of the pressure, both of the experimental in single dots and FDS. FDS is the fire dynamic simulator. I was not planning to go into detail. In one way or another, you have heard about that, but it's a computational software which is, at least in Sweden, 95% of the consultancy business is using it, and worldwide is used a lot. Why? It's free. So because there are other models which maybe could do more, especially on the ventilation part, which are commercial softwares. And so we tend to do. I think it's a good way that it is free, because it is supported by community. So it's not that I'm saying that it's wrong, but it automatically gives a large impact on the use. This was the pressure. Here you see both outlet and inlet. Then you see here that you get this kind of backflow, which you don't want. That means that the smoke goes into the air inlet, and unless you have not a way to cope with that, you will have smoke spread at the fresh side. You see that is coming back, and these are just results, and these are results to show that we are very honest at that. This is an overall picture of all the simulation. I think we did 25 to 30 different large-scale scenarios, and the peak pressures are generally within 20%, which means also it's not a perfect world. I don't want to give a picture that the models are perfect. The quasi-steady pressure was within 20%. The inlet flow in the beginning here, was sometimes wrong by 400%. That sounds a lot, but of course you have to think this is a dynamic comparison, and there are sometimes also in cases of both pressure and flows, you have smaller numbers. This is, like I say, over the whole range. As you see, if we would do this graphical analysis, you would say, well, it doesn't look so bad. You can hardly see where the dotted lines from both experiment and models are. So, so somehow the conclusions is for this, and now I'm looking to the time. Yeah, we started later also, so I always use that blame to somebody else. It's not the final conclusion, that's the problem. The conclusions is that this HVAC model is usable and I must say I'm very interested of the work done here, so I really hope we can cooperate in the future on this, trying to connect, let's say, more real-scale tests to the analysis of this model, because this is our one setup. Pressure changes and ventilation system behavior can be predicted, and that's good, because in the beginning of this Prisma project, we all did simulations where, and I'm a little bit ashamed that one of the simulations I did myself, what you did is you put the boundary condition of the ventilation of the test. So you had this curve, which I showed here, this curve, and this was put into the model as a boundary condition. And of course that gives you already much more better results, but it's not true, because in reality you will not get that data. You have to predict this behavior. So, but we managed to get to that. The inlet reverse flows are predicted, so you could detect, okay, there's a problem here with this scenario, with this type of fire, I get backflow. You also got very good indication in the model if you got into either a real underventilated condition or even into a kind of oscillating behavior where you get this back and forward, which is very tricky in case you would start opening these rooms. So, yeah, as I said, the only thing which I have to flag for or to warn is a bit that it's very sensitive to the loss factors inside the ventilation system. So you need to have somebody who's a little bit an expert on ventilation and pressure losses and so on. So, but else you can get this kind of simulation. But you see here we have a little bit more of a difference. Why I want to show here is just the levels of pressure. So in a mechanically ventilated room where there's very, very little leakage, the pressures are not as in a normal fire. So that means you see you can get up values of 1,000 Pascal or 2,000 Pascals, which of course in many cases might, if it's to the outside, break windows or something like that, but if not, you get very high pressures. And I know that yesterday there was also a session dealing with that if you had this combination of sprinklers, but it is without sprinklers. So while we try to show that to at least the research we do at our university is based towards fire safety engineering. So that we do try to do the fundamental research or applied research, but we also want to see that it can be used in the practice, so that it is not only that we're sitting in our little cube there in the south of Sweden and do this research, but that it can be used by our fire safety engineers. And for that we try to apply it on a multi-room residential building, which was picked up from, let's say, experience with some of the consultancy companies, and we did an evaluation of the soot spread between rooms. And we use different leakages here, and you can see depending on the leakage you get other levels of backflow. Here you got in principle that the fire dies, and then we used also growth rates in order to predict soot transport from one room to another. And what we did is that we used the common knowledge in Sweden what type of actions could be done in case of you have multi-rooms and you would run, for instance, the normal mode. You could shut down those fans and look what's happening. You get pressure reliefs and so on. I'm not going to list that because time is going out, but we used all these different type of strategies to this kind of 5-room setup with a fan system as it would be, at least in Sweden, not a strange situation. I have to explain a little bit that in Sweden we have rules where we allow certain leakage in case of fire between compartments or apartments, and then it's important to know whether that will happen. So this table, again, it's not in order for you to understand, but it just gives all the soot accumulated and all the difference. So it's a table for just an analysis that you can get this quite precise analysis of flows, soot levels, and so on. But that's also everything I want to show with it. It's just a little bit to impress you that we have done a lot, to be honest. But okay. Otherwise, it's only text and pictures. So the conclusion of this application is that we could use that for a typical residential building, so in preventing smoke spread. It's also to evaluate the performance of different systems by using this methodology of HVAC in FDS, so that you could have a better solution for a specific application, and also to identify the risks, both for, let's say, the occupancy, but also even possibly what's happening if there would be an intervention in such a case. And of course, evacuating is the first important thing, but also, of course, the fact that you want to know what's happening in these rooms. That's important for residential buildings, hotels, and so on, apartment buildings. In the nuclear power sector, you don't want this soot spreading around and destroying electronics and so on. So the overall conclusions I want to give you as a message, I hope I didn't get too much into the technical details, but I want to say that it's possibly also with models like FDS to simulate, let us say, the interaction of fire and ventilation for one room or multiple rooms where you have this kind of situation and scenario. There are practical engineering applications for that, which we can use these days. We have, at least in Sweden, and I don't know how the situation is in other countries, but in Sweden we have our own developed. In fact, it's developed at our university also by a ventilation professor, where you do these kind of calculations with a simple model, with a simple presentation of the fire. In this case, you can connect it to your scenario, where you can see all the other factors of a fire. That means smoke spread and so on in buildings, temperature analysis, and so on. We showed the application in buildings. If you want to, as I said, if you want to read a lot more and also know the interaction, that means the increase, because I didn't talk about the fire itself. I only talked about the ventilation and the reduction of the ventilation and the oscillating behavior and probably the starving of the fire. But there's also, of course, an effect that the fire growth, we want to predict that, because what we do now in FDS, we put in this kind of fire which is in the open environment, and then hopefully FDS covers with it through its models. But here, Jonathan worked also on trying to predict the so-called pool fire model. For at least the alumni students should know the, let's say, Babrowska-Speiler equations for pool fires. They are not valid anymore here in this situation, so you cannot use them anymore. So you can use that. I know it's a long, very long link, but if you have the PowerPoints, I guess they will be distributed. You just copy and paste. And I really want to say, look into this, especially if you're interested and you would work in the nuclear, to these two publications. The OECD project is a summary of two Prisma projects, so it means two projects of, in the order I said, 15-20 million euros, done by this international group. It's an open access report, it's an application report, so it gives you the results. It doesn't go into the big details of everything, but it's a good summary. It's anyhow a big report, but it's interesting, so you know the links of this work. And there's also a special issue in fire and materials, if you have access to that one on this Prisma project, which is based on mechanical ventilation, and I think is so. So, and I really hope that in the future that we can somehow work together with the people here to see how their experiments can be solved in FDS, and I think that was everything. I didn't see this 5 minutes, so I can continue if I want. So it's amazing that I'm in time. So.
Patrick, thank you very much, and nice in time. I give you 5 minutes per.
Yeah. Thank you.
No, you're welcome. Fire behavior. Ventilation rate, it's a very complex system, and it's very complex to catch in a model. It's a cost-expensive research you did, and mainly founded by the nuclear industry, I understood?
Yeah, I think this was, let's say, these main tests. The OECD is a quite complex financial situation, but it's partially OECD who puts in money, and then each member country which want to participate puts in money. We had to apply for additional money to do the modeling, and it's from this, let us say, the national funding then.
Okay.
But it's.
Well, I'm very happy that there are quite a few people, students, professors, who are gaining deep knowledge about modeling fire and smoke development. I think it's necessary for the future. And your figures, they impressed me. They did really impress me, what you showed me. Don't take modeling for as easy for reality if you didn't do a very good verification and validation. That's exactly. Also what you told us. Are there any questions in the audience for Patrick? Over there. Please, Patrick, can you help me and throw the the box to? Oh, you're better in football, you told me.
I get used to it. Good morning, Patrick.
Hey, nice to see you.
I'm not an expert in the field, but I'm surprised that FDS was chosen as the model for the HVAC system because it uses large eddy simulation, which is, as far as I know, quite correct for open field type of modeling, but not for the very enclosed systems like FDF. So I wonder, how did you make the model selection?
Well, I think the first thing is the very straightforward, honest, is that FDS has been used and already used a lot, of course, in the fire world, and also the reason why is that the ventilation model, the HVAC model, was implemented in FDS. And I know it's a large eddy simulation and there are restrictions, but by the correct, let's say, handling of the numerical setups and so on, you can get a good representation of the reality there. There are other models, maybe, which, as I said, could also be an alternative. But I'm going to be honest, much of our research is focused towards the practitioner, so that we really want to do modeling with something which can be used then also. And we see that there are, of course, certain limitations of using FDS, but that would be with another model also. So I think that's mainly the reason why we chose FDS.
The question arises because you worked a lot on the validation of the experiments. So then you would have come across the shortcomings, as you showed. And the obvious thing for me to do is then, did we have the right model?
Yeah. Well, I personally, now of course, you always try to defend your own research, so I'm very honest on that. But I think the thing is, what we try to prove here is exactly what you say, is that in the thesis there are done verification also, so that the model calculated correctly with other models, comparing and so on. So, but the most important thing is the validation part, so that you know that for that scenario you want to do, this was this nuclear power plants, but also room fire test, you could get and a value what would be, firstly, how good it works or how bad it works, and secondly also what are the possible differences. That means that you have an uncertainty, so which you know, are we talking about 10%, 20%, so we have values to use in the final safety assessment as such. I think that's quite important. So I'm very clear always, and people are forgetting that. We see all these models and all these fine simulations, and it's so important that you check, and it's an advice to everybody who has to check or to look into a computer simulation or an FDS simulation. Ask the question, how well is this model working for that scenario? Is there proof of any validation? FDS has this thick validation manual where you can look up, but you will have certain situations which has not been covered. And even that they have validated the model in this manual, you have to look what are the errors, because you will see, and they don't give any advice there that you maybe not should or not should use it. You have to make that decision. Is it good enough? So ask that question, what are the results of this model if a validation study has been done? And if you don't get a satisfactory answer, you have to question these models. Sorry, we model, but I think we have to give an honest message also, because then you have to see if the experiments can give you, hopefully, the right answer, because it's maybe also not a scenario.
Okay.
So,
thank you. Yeah,
long,
still filling
long
in the spare time.
yes.
Thank you for that.
I always say to my students to answer very long, so that it gets less questions.
One last question. No last question. Okay.